Okay, so graphically we know some terms. Now let's go back to our concentrations. So we looked at the concentration of ozone as it was going down. How would the concentration of the ethylene, the C2H4, change over that same time frame? Would the change look the same? Would it be a mirror image? Well, we know that the concentration of the one reactant is going to change stoichiometrically related to the other. So that means that every time I use up one ozone, how many of the C2H4s am I using? One. There's a 1-to-1 ratio between them. Now, if I had a different coefficient, if there was a 2 in front of that C2H4, then every time I used one ozone, it would be 2 of them. But in this case, there's 1-to-1. And so since it's 1-to-1, the rate of change of, the one is the rate of change of the other. These two are equal to one another because their coefficients are the same. Now, I may not have had the same initial concentration of my C2H4, so maybe I started with half as much of it, so the line was lower, but it would still mirror it as far as how it was changing. Or not mirror, but parallel. Okay, so let's take a look at a reactant here and some different stoichiometry. So we have 2 moles, reactions at the top, 2 moles of NOBr, and it's going to break apart and form 2 moles of nitrogen monoxide and 1 mole of bromine gas. So remember, bromine is one of our diatomics. Those are the elements that get together in pairs in their normal state. So as we lose 1 NOBr, as we lose 2 NOBr, we only get 1 Br2. So it's happening half as fast. The rate is half as much. And this should be a triangle, not a D. Sorry, forgot to change the font. So if I were to calculate in those first few seconds, how much, so I start off with 0.3 molar NOBr and no Br2 because it's a product. In the first 10 seconds, I change the amount of NOBr by this much, 0.038. That's how much that goes down. Now it's got a negative because it's going down. The amount that the bromine increases is going to be half as much. So 0.019 is half as much as 0.038. So they're related by half. Sometimes you'll get a question on tests about related rates where you have to compare the rate of one molecule to the other. You can usually get down to 2 choices if you remember it's a function of the coefficients. So one of those coefficients is going to say it's twice as much, and one is going to say it's half as much. So surely there's a formula that can help us remember how to do this. Oh, I forgot I had this in here. So this is looking at that graphically. So the NOBr goes down this much. This is where we have the mirror. The NO2 is rising. It's like I had a mirror right in here. They're exactly parallel. So this red one is the NO. But the Br is half as much. Okay, so that's graphically how I can see the difference between those. So if I were to look at the concentration after 10 seconds of the NO, the other product, it would be this 0.038 right here is the same amount that that one went down. Okay. So here's how we relate them. If I have a generic equation where the lowercase letters are the coefficients and the capital letters are the chemical formulas, so Lowercase a might be a 1 or a 2. Capital A might be my NOBR. Capital C might be my NO, and capital D might be my BR2. I can relate the rates in this way. So I find one of the rates based on I had a pH probe or I had the colorimeter. I'm able to figure out that rate. If I know this rate here, this part is the rate, in order to get from this rate to this rate, I'm going to set up this equation. Okay, so for each one, you have 1 over its own coefficient times its rate. But you have to remember that the rate doesn't include the coefficient. So if I'm trying to figure out what this rate is, I'm going to figure out this rate, divide by its own coefficient, and then this is going to get multiplied by this over here. So the numerical value of the rate depends upon the substance that serves as the reference. So it depends on which one we pick that we can measure. The rest is relative to it. So that's kind of convoluted in words. What does that mean? Just like every other conversion we do, divide by what you know, the coefficient, multiply by what you don't know, by what you want. So if I want to know the rate for the bromine, and I have the rate for the NOBR, I'm going to divide by the coefficient of the NOBR because I know that. And I'm going to multiply by the coefficient of the BR2 because that is what I want. Okay. So using the coefficients, divide by what you know or what you have, multiply by what you want. This is the same way stoichiometry works too, where if we think about if I know moles of my reactant and I want to figure out how many moles of product I'm going to get, I'm going to take my moles of my reactant, divide by the coefficient of the reactant, multiply by the coefficient of the product, and that's going to get me what I want. So divide by what you know, multiply by what you want to know. Okay, so here's a reaction, general reaction. In this case, instead of lowercase letters, we actually have coefficients. Remember, ones are invisible, so the coefficient for A and for D is a 1, it's not 0. All right, so we want to know the magnitude of the rate change for B. We already know that C is increasing at 4.6 molarity per second. The relationship between B and C, we got to put the negative sign in front of B because that one is the reactant, so it's actually decreasing. But all that negative sign is doing is telling us that when we plug in numbers, the change is going to be negative. I'm going to make it positive. All right, so we have this, but remember this part without the 1/3, that's the 4.6. What I want is delta B over delta T. So I'm going to take the 4.6, divide by the coefficient of C, that's what I have, multiply by the coefficient of B. The negative in there is just because B is decreasing. So when we get actual numbers, it's going to cancel out that change in B there being negative. And so we'll end up with 3.1. So what this means is that if you're looking at this on a test, pretend the negative isn't there. If you're comparing one thing to another, just pretend the negative isn't there. Just do the coefficients and don't worry about the negative. All right. What would be the rate relative to A? So B is 3.1, and I want to get to A. What am I going to divide by? By what I know. So I know B, what's the coefficient of B? 2. So I'm going to divide this by 2. That's going to give me right about 1.6. And then I'm going to multiply by the one I want. I want A. What's the coefficient of A? 1. So we just end up being about 1.6. What if I started at C? So C was 4.6. And I wanted to go to A. So I'm going to divide by what I know. Coefficient of C is 3. So 3 going into 4.6 is going to give me 1, carry the 1, 1.55. Right about the same thing. Okay. I'll try and give you another example of that on Monday. I think this is the only example I have in here right now. Okay, so all of this is to try and come up with a rate law. Rate laws help us to understand what's actually happening in the chemical reaction and how can I use that to speed up a reaction, to slow down a reaction, those kinds of things. So if I don't want a reaction to go, what's the easiest way to slow it down? I can look at the rate law. If I do want a reaction to go faster, what's the quickest way to speed that up? So the rate law is going to incorporate all of the concentration dependencies, not just one. So it's not going to be just the rate relative to A or just the rate relative to B. It's going to incorporate all of them. Now we typically look at just the reactants. In this class, we will only look at reactants. If you get into more advanced chemistry, you will find out that products can sometimes have sort of a feedback where they slow down a reaction or maybe they speed up the reaction. So they can be inhibitors or they can be catalysts depending on what all is going on with the reaction. We're going to keep it nice and simple. We're only looking at the reactants. Okay, so generic thing here. Lots of reactants with their coefficients, could be any number, forming lots of products. Okay, so in this reaction, we would write the rate law as rate is equal to, and it's going to be K. Now, it's important that this is a lowercase k. When we get to equilibrium, we're going to use a capital K. I don't make the rules. I know it's confusing, but this one's a lowercase k. This is not Henry's constant that we just did before. This is a constant that is specific to whatever reaction we're looking at. Okay. So it's going to be the concentration of each reactant raised to a power. Is it being raised to the power of the coefficient? Like, is A raised to the power of the coefficient of A? No, we're using an M and not the little lowercase a, right? So the order of the reaction, which is what that exponent is, the order of the reaction is not the coefficient. Now, sometimes it works out to be the same thing, but unless it is just a very simple one-step reaction, it's just coincidental that it works out to the same thing. So that means if the coefficient of A is 2, I could have the exponent be 1. And if the coefficient of B is 1, I could have its exponent be 0. So in theory, these could be a lot of different things. We're going to focus on 3 possibilities, 0, 1, and 2. Anything beyond 2 almost never happens. Definitely beyond 3, it wouldn't really happen. But beyond 2, it doesn't really happen. 0 means that how much I have of that particular chemical doesn't really affect how fast that rate is going. So sometimes with rates, I use the example of doing laundry. And if you are doing your laundry and it takes, say, 35 minutes to run a load in the washing machine, but it takes an hour to do it in the dryer. And let's say you only have one of each. So you have to do washer and then dryer, washer and then dryer, washer and then dryer. Well, it's the amount of time it takes you to do stuff is going to depend on the dryer. If I am washing my loads in 20 minutes instead of 35, it's still not going to change how long that thing has to be in the dryer. Okay, so that would mean of those 2 things, the washer isn't really involved in the rate. And so since it's not really involved in the rate, it would have an exponent of 0. So if I take a number like 2 and raise it to the 0, what is that? 1. If I have 123 to the 0, what is that? 1, right? So no matter what that is, this is 1. And when I multiply 1 into that equation, it's basically saying I'm not important. I'm not really involved here. Okay, so let's say we have this rate law. So that is not a negative. That is just a dash the way that PowerPoint is doing the bullets. So rate, with no negative in front of it, rate is equal to K, which is specific to this reaction, times the concentration of A to the first power times the concentration of B squared. Okay, so K is the rate constant. You can't figure that out just by looking at the chemicals. Somebody has to run the experiment and do the tests and measure the concentration. Remember, in the square back brackets, that means those are the concentrations, the molarities, and that's at a specific time in the rate. So usually we're looking at the initial. And then the exponents are what we call the order with respect to the reactant. So the order with respect to A is the invisible 1. The order with respect to B is 2. And the order with respect to C is 0. Now, C doesn't appear in there, but remember that if I had C in square brackets with a 0, that would turn out to be 1. And again, 1s are invisible in chemistry, right? So anything other than A and B, the order with respect to that thing would be 0. So we have for each thing, the order, and then to find the overall order, we just add them up. So we would add 1 plus 2 plus 0. The overall reaction order is 3. Make sense? The math in this part, simple. Just got to keep track of the terminology. Okay. And then first part of this is just what I keep saying. If it doesn't appear, the reaction order is 0. So that's like that C there. And the reaction orders have to be determined experimentally. So I can't just like look at a reaction and know what it is based on where it is on the periodic table. I really ought to change this rate to be the same as the one before. I had in my mind it was just going to be a different reaction, but it looks so similar to the other. I should just make it the same. All right, so I think that is a good place to stop. Questions about this? We got a couple of minutes. Ask me 2 questions before you. Yeah. What does reaction order mean? So reaction order is not really order in the terminology that we would use it in everyday language. It's not sequencing something. It is just telling us how what that exponent is. And what that is telling us is we'll ultimately find out how many molecules are colliding at the key point of the reaction. So if I have, like I have here, a 2 and a 1, this tells me that at the rate determining step, I have to have 2 molecules of A and 1 molecule of B. And that's why we don't really see anything above a 2, because the odds of being able to consistently get 4 molecules or more together in just the right way are just astronomically low. So there just really aren't reactions that have orders above 3. All right, that was one question. Yeah.
Why did they write the equation? I mean, an A squared and B. Like, is there like a specific reason? I mean, it's kind of
Like as opposed to what?
Shorthand for like chemical reaction, but like why did it?
Because this chemical reaction could have been A plus B plus 2C. So remember that these aren't coming from the chemical reaction. This is telling us the rate, and this is actual numbers that I can plug in. So if I know this is 0.5 molar and this is 0.2 molar, and that doesn't matter what it is, and this rate constant is 1.7 times 10 to the negative 7, I can actually plug those in and have a numerical rate. So it actually corresponds mathematically to what's going on. And we'll see that with the reactions. All right. That sounds good to me. Have a good weekend. Get out there and play, but don't forget to do your vocabulary.